for a hot weather like Saudi Arabia, I found the need to explain and talk about temperature right now, the physical quantity. Starting by the fact that temperature comes with four common temperature scales: degrees Celsius, Kelvin, Rankine, and Fahrenheit. These scales are existed to ease our lives and explain our feeling as well. Before explaining the equation that relates the four of them together, I would like to ask you, if you wanted to describe a story of how hot the weather is today, would you say the weather today is far from boiling point of water but high in a way that it won't let me productive? If you said a story like that to someone, believe me, he or she would throw anything on you just to stop talking forever. On the other hand, if you said that the weather is 40 degree, it will immediately explain your feeling and deliver the idea that the weather was unbearable. That's why you need these temperature scales. They describe the meaning of the number. If I said 100 degrees Celsius, it is so hot. It is hot that we can't live anymore in this weather. If I said 0, it is so cold. If I said 50, it's like an oven. It not only describes our feeling but also gives reliable and accurate measurements. When you go and work in industry, you need powerful, immediate numbers that are meaningful and provide you valuable conclusions. And now with the four equations, if you want the temperature in Kelvin, enter the number of the temperature in degrees Celsius, add to it 273.15. If you want to find the temperature in Rankine, just insert the number in Fahrenheit, add to it 459.67. If you have the temperature in Kelvin and you want it in Rankine, then you will say T equal to 1.8 times the temperature in the Kelvin that you have. And lastly, if you want to find the temperature in Fahrenheit degree, given the variable or the quantity of temperature at degrees Celsius, just add to it 32. What you notice about these four equations is the fact that all of them are related in a linear fashion, which makes our life so much easier, other than the fact that they are used to describe the meaning of a number. And now let's focus on number 3 and 4. If you are doing dimensional analysis, you would say that this 32 has to be in Fahrenheit in order to make all of them Fahrenheit. It means this term has to be in Fahrenheit, which means this 1.8 will have a unit of Fahrenheit divided by degrees Celsius. The same thing here. Number 3, you will have 1.8 in units of, like what you guessed it, Rankine over Kelvin. To cancel the Kelvin with Kelvin, ending up having only Rankine. For numbers 1 and 2, though, you might say, how do we have here degrees Celsius and here Fahrenheit, even though the equation has to end up with Rankine, or in this case here, has to end up with Kelvin, right? For number 1, there is number 1 here hidden. We do not usually write number 1. We ignore it. But here actually there is temperature times number 1. This number 1 has a unit of Kelvin divided by degrees Celsius, to cancel degrees Celsius with degrees Celsius. Similarly, with number 2, you have this number 1 hidden here. We do not write it, but it represents the relation 1 Rankine divided by 1 Fahrenheit. What I have written in these four relationships are something fascinating. Interval. So a degree, whether if it was Kelvin, Rankine, Fahrenheit, or degrees Celsius, they consist of a specific number or equivalent, or they consist of interval. I'm a huge fan of illustrating a certain concept by an example, so let's do it now. Recalling the 40 degrees Celsius, we want to know what is it equal to in terms of Fahrenheit, Rankine, and Kelvin. Starting by equation 1, T in Kelvin is equal to T in Celsius, which is 40. Add to it 273.15, 313.15 Kelvin. We want to find it in Rankine, number 3, is equal to 1.8 times T in Kelvin, which we found, and the answer should be in Rankine, 563.67. If you want to know it in Fahrenheit, number 4, T in Fahrenheit is equal to 1.8 times the temperature in degrees Celsius, add to it 32, and the answer 104 Fahrenheit. This example, we show how to find the equivalent, but if you want to find the interval, then it means something else. Future data that you might face could include some temperature range, say from 20 to 40. You would know that here you have 20 temperature between 20 and 40, because if you subtract, then you will have 20. But how would you know in degree Fahrenheit, for example, or in Rankine, or in Kelvin? You would need to convert, not in the same equation as we used here, because these are the equivalent. I have a temperature in 40, I want to find out its temperature in Kelvin, for example. Specific, equivalent number, not an interval. Here I want to find how many Fahrenheit from 20 to 40 degrees Celsius. That's the meaning. In this case, you would use a conversion factor from degrees Celsius to Fahrenheit. 1.8 Fahrenheit is equal to 1 degree Celsius. If the range is 20 degrees Celsius, degrees Celsius in the denominator to cancel with degrees Celsius, ending up having Fahrenheit. The answer will be 36 now. It means that if you have a data in Fahrenheit, then the range that you are dealing with will include 36 number in Fahrenheit. 2 Fahrenheit up until you reach 38 Fahrenheit. This is the interval that includes the temperature of the Fahrenheit from a certain number to a certain number. For example, from 100 to 136 Fahrenheit. The range will be 36. It's not a specific number, okay? If you want to find the range in Rankine now, use the conversion factor. 1 Kelvin is equal to 1 degree Celsius in terms of interval. I want to know the range in Kelvin. I will say 1 degree Celsius for each 1 Kelvin. But I want to convert from Kelvin to Rankine because I want Rankine. So I will say for each 1 Kelvin we have 1.8 Rankine. And the answer will be 36 Rankine. And now you will notice a very nice rule here. Kelvin range is equal to degree Celsius range. If I have a temperature range 20 degrees Celsius, it will be 20 Kelvin immediately. And 1 Fahrenheit range is the same as 1 Rankine range. If I have 36 Fahrenheit range, I will have 36 Rankine range. Kelvin with degree Celsius, they have equal relationship, but 1 degree Celsius, the range that you have in degrees Celsius, you would multiply it by 1.8 to find the range in Fahrenheit. Similarly, the range in Kelvin, you would multiply it by 1.8 to find the range in Rankine. These are conversion factor. These are exact numbers. I have a specific number of temperature. I want to find its equivalent, not its range. Here I have a range of data that contains the temperature, and I want to know this range with another unit, so I will use this conversion factor to know the range in different temperature scale. And now we come to the engineering part, where we ask ourselves how to measure the temperature, starting with thermocouple. In fact, thermocouples that you will use, it is consisted of 2 metals, a wire A or metal A and another wire metal B. These 2 metals are connected to a terminal block where it displays the positive and the negative charge of these wires, and the other end contains connected part. This is called hot junction. This is called cold junction. This terminal block is connected to a multimeter or temperature controller, or we call it simply meter, that shows a display of the difference between the wire of A and wire of B. And this difference is measured in the unit of volts or millivolts, because the difference will be small usually. Here is the voltage reading. It's connected voltage, not voltage, but because I don't have a space. This difference is related to the temperature that we want to find by using what we call thermoelectric equation. Don't be surprised to see some graphs that contain the voltage with respect to temperature to read off the value of the voltage that corresponds to a value of a temperature. What we are interested in right now is the fact that we use thermocouple to measure temperature through usage of voltage. As you increase the voltage, you will increase the temperature. But I have to mention though that this voltage will not display any number. It will be 0 if you did not expose some heat to the thermocouple. So here you usually expose some heat, and this heat will cause both electrons in the wires to move far away from the heat, so they will be here somehow. And the rate at which the electron of A moves and the rate at which the electron of B moves is different from each other, and this is why actually it causes some voltage reading here. And this is why we are saying thermocouple is consisted of two different metals, because if they are the same, then you will have no reading here. We have to have different rate of moving electrons for A and B so that the reading is shown. The other type that is most commonly used, even though I put it as number 2, I don't know why, thermometer, is actually used in laboratory as well. A thermometer comes with two types of liquids. It has a shape like this, and inside it we fill some liquid. Not all of this, just some portion here. This liquid could be mercury. If you recall, I told you before that mercury has wide applications. This is one of the application. Or could be alcohol as well. And this is actually one type of thermometer, the type that we fill it with a liquid in a glass. And then we insert it in, for example, if you are working in a laboratory, small scale production, you will put it inside a beaker. This beaker contains some liquid that we want to find its temperature. If you put this thermometer inside this beaker that contains the substance whose temperature you want to find, then there will be expansion that will make this liquid inside the thermometer goes upward until reaching to a certain point, and this point will be read and then record the temperature. This thermometer has a scale written on it. If you zoom on this thermometer, you will have reading for each 1 degree, and so if this liquid rose, it would rise to a place that we know its temperature because this thermometer has a scale on it. This is one type of a thermometer. We have also digital, we have other types of thermometer, but this is the most used one. I should mention though that for safety reasons, we don't use mercury and take it for granted because mercury has some of the toxicity inside it. So we need to be very careful about using the mercury and also alcohol, even though alcohol is not harmful as mercury. But mercury has wide application, it has a high coefficient of expansion. This will create an excellent reading of a temperature value. So we use it with carefulness. The last type I want to mention is the pyrometer. It has a very simple yet complicated in practice working principle because it's about having an object which could be liquid, solid, like a metal, and depending on the amount of infrared radiation that are emitted by this liquid or this solid, the pyrometer will take this infrared radiation and calculate or use it to calculate the temperature. Few things to mention about pyrometer is the fact that of course it should be turned on, it should have a battery, and it will just do the work of calculating the infrared radiation by the liquid or by the solid to use it later on to find the temperature. We spent a lot of time talking about temperature. This is actually the whole thing about the 12th drug. When it comes to the 13th drug though, it doesn't know anything but pressure. As always, we start slow. Pressure is defined as the force exerted divided by the area. In terms of dimensional analysis, force if it is Newton and area if it is meter square, then we will have Pascal, which is a derived unit because it came from 2 or more units as we said before. Newton comes with many units inside it. Meter square, it's a compound unit, meter times meter. This equation, physically speaking, means that if you have tube like this, the U shape for example, and you applied a force, so you applied some force, this force that is exerted on this tube that has a U shape divided by its area will be the pressure at this point. Now going back to Pascal, usually the answer of a pressure in terms of Pascal will be to the scale of 10 to the power 5 Pascal, because Pascal is very very small in comparison with the atmosphere. One atmosphere, believe it or not, is equal to 101,325, so it's about 10 to the power 5 Pascal, which is equal to 101.325 kilopascal. We convert from Pascal to kilopascal to atmosphere, and we usually express pressure unit in terms of pound per inch square, or according to the abbreviation, it's pound per square inch. It's the same meaning. 14.7 of psi is equal to 1 atmosphere. We express pressure also in terms of height of mercury, 760 millimeter mercury, and I saw some cases of 10.336, if I recall, meter of water, but this is not common as mercury. So these are conversion factors that you may need to use whenever you are dealing with pressure. As for the pressure calculation method, then it's not a coincidence if I draw this shape, because it's actually what you will face when you deal with liquid column method. An example of it, manometer. Manometer comes in 3 different types. We have open end, and we have differential, and the last type is sealed end. Open end has a shape like this. Excuse my drawing once again. We have a pipe like this, and there is a construction. It's a similar way when we talked about the orifice meter type. And now we fill this with mercury, because as we discussed before, mercury has an excellent reading of temperature or of pressure. This is mercury. It has a symbol of Hg here. And this is usually open to the atmosphere, which is 1. But it's not always 1 atmosphere. It's only 1 when we are at sea level. And the other end, it's to the system being dealt with. This system contains a fluid that we want to find its pressure. If you notice here, we have an equal height from this point up to this point. And according to Pascal's principle, whenever we apply a force or a pressure, they are related. In a confined space, like from this point here up to here, these 2 points that have the same height, then the pressure from this point will be transferred equally to this point. And so when we calculate the pressure at point 1, this point, we can ignore the pressure transfer from here up to here. And you can only focus on this area, just this area. If we know its height, and if we know the atmospheric pressure, we can find the pressure of the fluid we want to find its pressure. It's equal to the atmospheric pressure, 1 atmosphere if we are at sea level. Add to it what we call pressure of the mercury. But this pressure of the mercury, which is this point only here, this is called hydrostatic pressure, which is equal to the density of the mercury multiplied by the acceleration due to gravity, and then the height should be small, h small. Why rho of mercury? Because the fluid here is mercury. Few things about pressure. As we go down, pressure increases. If we are going upward, then P will decrease. So if you calculate this pressure, you would expect the value to be negative. Be careful though that this has a unit of Pascal, and this has a unit of atmosphere. So you would need to do conversion factor to convert from atmosphere to Pascal or Pascal to atmosphere, or use what we call pressure head equation. Pressure head equation depends on mercury height, and it is much simpler approach to this one, because all you have to say is overall height of the fluid at point 1 in millimeter mercury, just equal to the height of the mercury here. This millimeter mercury is a unit. This pressure is not the pressure of the mercury, no. This is the pressure of the fluid in terms of a millimeter mercury unit. Here, the pressure of the mercury in terms of millimeter mercury. Add to it the 760 millimeter mercury. If you recall, 1 atmosphere is equal to 760 millimeter mercury. And you will find the answer in terms of millimeter mercury. Convert to atmosphere, convert to Pascal, and the answer that you will get from this equation, it will be exactly the same as this one. Simpler approach than this, but all give the same answer. And this will be easier if you just pay attention to the units here. The other type of the manometer is the differential pressure. And from its meaning, or from its name, it means that we will measure the difference of pressure, which is P1 minus P2. Just a quick drawing. A pipe like this case, but bigger like this one, and then not open to the atmosphere. Both ends are connected to the system, and we want to find the difference now between P1 and P2 in this fluid. A fluid up to this point with a certain height, call it H1. This point here will be ignored according to Pascal's principle, or according to one Italian guy, If I recall its name, it was Torshili, maybe. So anyway, we'll ignore this region. We don't know the pressure at both ends. So we will find that pressure drop, or the pressure difference, rho of the fluid minus rho multiplied by the acceleration due to gravity times h. You would ask me, what is this density? This white color is another density, hw, h white. So this is hw from or for the density of the white fluid, and this h1, this h2 for mercury. And this white one also has this region also. So hw1, hw, h1 or h2, both of these white densities are the same. And in this case, we will say that P1 minus P2 is equal to rho of the fluid, F, mercury, minus the rho of the white one, all of them multiplied by GH. So in this case of differential manometer, you will need to find the pressure drop, not the specific pressure at certain point like this one. Because this one is open to the atmosphere, we know the pressure of the atmosphere at sea level. And the last type is the sealed end. In fact, just close this portion and you will have the sealed end type. The fluid here, the construction, this is closed, and we have the mercury, for example, here. This is closed, and this is here white, and this white is no atmosphere, 0, because we have nothing here. And this what we will call later on vacuum. Consider the case now if P1 is not the pressure of the fluid we want to measure, but rather it's the pressure of the atmosphere. So if this hole or if this end is open to the atmosphere, then we call this case of sealed end manometer barometer, a very famous name that I'm sure you have heard of. But if not, it's fine. We can introduce it now, and we will introduce it surely in fluid mechanics. All of these, in fact, pressure measurements, we will go in details. Here, just an introductory course, chemical engineering principles. So you will take a portion from every side, this one P1. And P1 will just be similarly like this equation. It will be P1, the pressure we want to calculate, not in the barometer case, no, it's in the sealed end case, where P0 is equal to 0 and P1 is the pressure of the fluid. It will be rho of this white fluid, G, and then H of this height. And we are going downward, so it will be positive. And then ignore this region. And because we are going upward, it will be negative rho of the white fluid, which is the same as this one, multiplied by G and then multiplied by H, W, the height of this region. Wanna make it fancy then, and the unit is in Pascal, you can convert it later on using these conversion factors. As for the barometer case, then we will most likely use it whenever we want to calculate the atmospheric pressure. Some cases, it's not enough to say that the atmospheric pressure is equal to 1 at the sea level. Maybe we are calculating the atmospheric pressure not at sea level. It will be lower because we are going upward and we need the barometer to calculate the pressure. And now let's expand our horizon a little bit. If we want to calculate the pressure but not in a 3 atmospheric range, surely in industrial scales we will end up having a pressure of greater than 3 atmosphere, most of the cases. So using manometer might not be enough because it cannot withstand this high pressure of 3 atmosphere. And in that case, we would need to move on to one of the most used type of pressure measurement device, which is called gauge. It is reliable, it is simple, and it needs to be calibrated. Most of the devices that I will mention consider calibration the first thing to do, because calibration makes us trust the machine. How can we trust the machine? How can we use it if we do not calibrate it, right? So this Burden gauge has a C shape, and then there is a rack. It's a mechanical device, so it makes our life easy. We have a linkage that relates this rack with the Burden tube. This is Burden tube. This is the linkage, and this is the rack. This line is segmental lever. There is a flow, and this is connected to this machine in a way that whenever there is a flow here, it will enter this region. There is a constriction, so there will be a pressure, and this fluid pressure will come to this machine. If you zoom on this machine, a circle, and then the readings, this is not the sun, and then there is a dial here, and this dial is set as 0 until there is a pressure of the fluid coming to the side of the burden gauge, and this is the opening. This is the shape of the burden gauge, but I zoomed in it. There's a fluid. This fluid will enter. Because of the pressure existence, this link will move in a way that makes this rack move, and the dial then therefore will move, and it will give us the reading that we want. Some of the things I mentioned without illustrating their meaning were vacuum, gauge, and the absolute pressure. I talked about atmospheric pressure, and actually atmospheric pressure and gauge pressure allows us to find the absolute pressure. Just add these together. Whereas vacuum and the gauge are related to each other, if you have a negative value of gauge, then it means a positive value of vacuum. I will talk about them in the next video as an introduction, and move on to the story that has been delayed for a long time, which is the story of moles.